Okay guys, I've decided to record this video because we're not going to have classes on Monday, right? So let's first review what we need to solve problems which I'm planning to discuss today. Right. So first of all, this is chapter 11, where we're still discussing linear momentum, right? Okay, so first of all, let's assume that we have, I will put a first bullet, one object. Our system is one object. And of course, we assume that the motion is one-dimensional, right? Let's say this is my x-axis. Let's assume that this is my object, right, of mass m. It can move with velocity v, let's say this way, velocity v, right? And in the previous classes, we introduced a new quantity, right, which we called a linear momentum, right? So we introduced this quantity, we call it p, and by definition, 3 lines, we denote it as m times v, right? So this is linear momentum. Right. So let me frame it. Okay, it's one of the most fundamental quantities in physics. Then, let's assume that there is a force acting on this object. Oh, for example, let's say we have force F acting on the object. Of course, if there is a force, the state of the motion of this object will change, right? So how to describe that change? Of course, we use Newton's second law. In the past, we used this form of the Newton's second law. Okay, let me use net force acting on the object equals mass times acceleration. That's what we used in the past. But as I told you in the lecture, this form of the Newton's second law is not capable of describing, for example, motion of an object which mass changes as the object moves. So in order to describe motions like that, we rewrote Newton's second law in the most general form. Right. Okay, so the most general form of the Newton's second law, net force acting on the system, on the object in our case, equals to the rate of change of this linear momentum. Right. Okay, so that is the most general form of the Newton's second law. Right. So I will write Newton's second law, and I will write general form. Okay. Now let's make our system more complicated. Let's add additional object, right? And these two objects they're going to interact, right? Colliding, pushing each other, pulling, right? Whatever, any forces of interaction. And again, we were going to assume that our system moves along a straight line, so one-dimensional motion. So now I will put another bullet, and I will write, now let's assume that we have two objects. So that's our system, which we are going to describe. Right? So again, it's a one-dimensional motion, so I will introduce x-axis, and let's assume that we have, this is the first object, let's say mass m1, and here's the second object with mass m2, right? We can also assume that they have some velocities, right? I'm just making it up, right? So this might move with this direction with velocity v2. This guy can move this way with velocity v1. Then, of course, they interact. So this guy will exert force on the second one, right? And we can represent that force using this vector. Let's label it. So it comes from first object, so first subscript is 1, the second subscript is 2. So the force is being exerted on the second object. Of course, at the same time, according to the Newton's third law, there must be a force of the same magnitude, but opposite in direction F to 1. these forces, F21 and F12, we call internal forces because they act within the system. So objects within the system exert these forces. So that's why we call them internal forces. F12 and F21 are internal forces. But it's also possible that there's a force from some object which is not part of our system. For example, the Earth. The Earth is not part of our system, which we try to describe. So that force which comes from the Earth is the external force. Right? So in this case, for example, gravitational force will be the external force. Okay, let me draw it. So let's say this is F1 external. So external force acting on object 1. And of course there will be external force acting on object 2. Oh, the other way. External upper script. External 2. Okay, so we might have 2 or more external forces. Okay, then. So if we have 2 objects, these have a certain linear momentum, these can have a certain linear momentum, so we can introduce the total linear momentum of the system, of our system. We can introduce total linear momentum of the system, right? So let's, P capital, I use to denote total linear momentum of the system. Bar underneath, it means that this P is a capital P. So we can write as P1 plus P2. So these two P's, they are small p, right? Because there's no bar underneath. Of course, we can write it as using definition of the momentum, mv1 plus m1, m2 v2. Okay, then, in the previous lecture, we showed that if you look at the rate of change of the total linear momentum, this P capital, if we look at the rate of change, which is dp over dt, rate of change of the total linear momentum, so it is equal to not all forces acting on the system, but only equals to the net external force acting on the system. So summation of F external. Wait, vector sign in the wrong place. Right. So, so that's what we can use to describe a system, for example, of 2 objects. So internal forces, they cancel each other out of the game right now. So only external forces can play this game if we want to know the rate of change of the total linear momentum. Right. So internal forces are not capable of changing the total linear momentum of the system. Okay, so let me write that the internal forces, forces cancel each other. Cancel each other out. So that's why, for example, if I take this ball, of course, inside of this ball we have gazillion number of particles, and they of course interacting with each other, right? And if I leave it like this, right? So right now the total linear momentum is 0, and of course, there are tons of internal forces, but those internal forces are not capable of changing that 0 linear momentum. As a result, this object is going to be lie down like this forever and ever. It is not going to start moving by itself because internal forces are not capable of doing this. Internal forces every time cancel each other out. So only external forces. If I apply my external force, of course the object will start moving, right? Okay, so now, important consequence of this. So there are situations, actually they happen quite, it happens quite often, when this external force, net external force, equals to 0. So if net external force equals to 0, then rate of change of the total linear momentum is 0, and it means that P, total linear momentum, must be constant. Constant throughout the whole motion. It means that total linear momentum is preserved. So as a result, I can write that P is constant. So which is conservation of linear momentum. Okay, all right. All these quantities are vectors. Of course, we can talk about the conservation of linear momentum along x direction or y direction. It's possible that linear momentum is conserved in x direction but not in the y direction. Or vice versa, it can conserve in the y direction but may not conserve in the x direction. So I can write also this way. If net, to erase this, if net external force in the x direction equals to 0, then total linear momentum of the system in the x direction will be constant. So I can write that P, which way I should write, x initial equals to P x final. So I can compare, for example, total linear momentum of the system at this moment of time with total linear momentum at that moment of time, and I can solve problem of finding, for example, something at the final moment of time if we have enough information about the initial moment of time. And the same I can write about the y direction. If net force, of course external force, wait, I shouldn't be writing vector sign over here because now it's along the x direction and here the same. In the y direction equals 0, then of course I can write that total linear momentum at some initial moment of time in the y direction equals to the total linear momentum at the final moment of time in the y direction. So that's what we're going to use. Most of the time, of course, our linear momentum will be conserved along x direction, so of course we're going to use that. And every time we will be checking if this statement is true. So now let's look at a few examples. So let's start with the problem, which one? 11:15. Okay, I will separate like this, right? So let's start from 11:15. So chapter 11, problem 15. So what do we have here physically? So we have a railroad car, right, which moves with a certain initial velocity, given velocity, right? Let's say 2 meters per second. Then, at a certain moment of time, a load of gravel is dumped into the car, right? Of course, the load is just released, right? So it doesn't have any horizontal velocity, right? So, and of course, when load gets into the car, of course, the velocity of the car gets smaller, right? So we need to find that final velocity of the car, right? So that's the situation. So now let's draw this situation, right? And then we'll start discussing it deeper. So, first of all, our system. What is our system? Let me write. Our system is a car and a load. Right? So that's our system. Any object which is outside of this system is the external object. Right? Motion is one-dimensional. Right? So I will introduce x-axis. Right? Let's say this is my x-axis. Right? And here is my car. Okay, couple of wheels. Right? Two pairs of wheels. Right? And here's the load of gravel. Right? So let me write. So this is load. Let me label it as M sub L. M sub L. L stands for the load. And mass of the car, of course, M sub C, mass of the car. Then, what also given? The initial velocity of the car, right? So V, let me label it as C sub I. C sub I. Yeah, and I will probably write 2 meters per second. Then, of course, initial velocity of the load in the horizontal direction is 0. Of course, it's not 0 in the y direction. So V load initial, of course, 0. So that's our initial situation. That's our initial situation. All right. So I stands for initial. Now let's draw situation after the collision, right? After load is dumped into the car. So now after the collision, again, it's still one-dimensional motion. Of course, car might have moved slightly, right? Let's see, this way. Right. And the load now is inside. So this is our load. Okay, let me label them. So it will be mass of the load, and of course, mass of the car still there, right? So now, and of course, the velocity will be different, Vf, and that's what we need to find, this final velocity. Of course, a load and the car are going to move with the same velocity. Right, so that is our final situation. Okay, let me write down what is given. Okay, I don't remember the numbers, so I need to use my notes. All right. What is given? Mass of the car is 10,000 kilograms. Then mass of the load is 4,000 kilograms. Yeah, and velocities. Velocity of the car initial is 2 meters per second. And of course, velocity of the load initial is 0 because the load was not moved, or did not move in the horizontal direction. Anything else? No, that's it, right? So now we need to find, what do we need to find? Vf final velocity. That's what is given. Okay, all right, we have two objects moving in the horizontal direction. Of course, they're interacting. Of course, load will exert force on the car, and the car will exert force on the load. But those forces are internal forces, right? And they're not capable of changing the total linear momentum of the system. Right? So we need to look at the external forces in order to come up with a conclusion if linear momentum is conserved or not. Okay, I will look in both directions, in the y direction and x direction, in order to just show how can you justify the conservation of linear momentum. So let me start first with the y direction. Let me put y, circle it, and which way I should write? Okay, rate of change of the total linear momentum in the y direction equals, of course, net external force in the y direction. In this case, let's look at the all external forces acting in the y direction. The car. All right. Of course, there is a force of gravity, but the force of gravity will be balanced by the normal force from the ground. So net force acting, net force in the y direction acting on the car is 0. Then, what about the load? For the load, different situation. Load will experience, of course, force of gravity, which is an external force, which is not balanced by anything. So it means that there is a net external force. This force of gravity acting on the load will be an external force. As a result, this side is not zero because of that gravity. And as a result, total linear momentum in the y direction is not conserved. So from here I can write Py is not constant. But we don't need it, right? Because we will be able to solve the problem looking at the total linear momentum in the x direction. Okay, so now let's justify the conservation of linear momentum in the x direction. So x, the rate of change of the total linear momentum equals the net force, net external force acting in the x direction. Okay, on the load, in the x direction, horizontal direction, there are no any forces acting on the load in the x direction, right? Then, car, of course it's possible to have friction, but let's assume that we have a nice track, we have a nice wheel, so we don't have any friction in the x direction. And of course we are going to assume that air resistance is small. It's a very good approximation. Right? So we can write that this is 0, right? Since there is no friction, there is no friction. Right. So net external force equals 0. As a result, the total linear momentum in the x direction must be preserved, must be constant. Okay, so it means that Px equals constant, or in our case, let's compare total linear momentum in the x direction before this collision and after initial and final, at the initial and final moments of time. So I will write here, so it will be P total linear momentum in the x direction final equals, let me start with the initial. Yeah, let me start with initial. Initial, right, equals total linear momentum in the x direction final. Okay, it's initial. So that's initial, I mean, this is the sort of like a starting point, so conservation of a linear momentum in the x direction. So now let's write down explicitly the total linear momentum at the initial moment of time and the final. Of course, it consists of linear momentum of the load, P, and the linear momentum of the car, P car initial plus P load initial. That's the total linear momentum before the collision. And now, of course, I can write similar after the collision. But now both of the objects move with the same velocity Vf. So I can factor that out. So I can write as m car plus m load V final. Right. And the total linear momentum of the car final plus total and it is equal to linear momentum of the car final plus linear momentum of the load final. Right. Okay, so now of course we know the definition of a linear momentum. It's a mass times velocity. Of course I can write explicitly. So it will be m car v car initial. And look, we know from the statement of the problem that this car moves to the right, which I choose as the positive x direction. So our velocity as a result, and as a result our linear momentum is positive. That's why basically I put here plus. If my car moved that way, in the negative x direction, of course I would put here minus, because that's what is given in the problem. But here it is plus. Plus mass of the load and initial velocity of the load, which is of course 0. We will dump it in a second. And velocity final of the car and the load exactly the same, so I can factor it out. So I can write mass of the car plus mass of the load times velocity final. Okay, let's remove this initial velocity of the load because it is 0. Right? And let's see, that's what we need to find. That's our question. This is given, this is given, this is 0, and given and given. So problem basically solved. We just need to solve it for v final, and it is done. Let me continue it here. So v final would be equal mass of the car, velocity of the car initial divided by mass of the car plus mass of the load, right? So that's our final result. So now let's plug numbers, right, to get the answer, right? So of course mass of the car 10,000 kilograms times velocity 2 meters per second divided by 10,000 plus kilograms plus 4,000 kilograms. Right. So the answer will be, let me look at my notes, 1.4 meters per second. 1.4 meters per second. And you see the answer is positive. Answer is positive plus 1.4 meters per second. It means that our system load with the car moves in the positive x direction, right? If at the end we ended up, let's say, with minus 1.4, of course it would mean that system would be moved in the negative x direction. But of course in this case it's positive and it moves in the positive x direction, which makes sense. We know it from our everyday experience. Okay guys, let's continue, right? The next example which I want to discuss is 1129. Again, chapter 11, problem 29. So where we have this situation. We have two skaters on a circular skating ring, right? First, initially, they're standing at the very center of this ring, holding their hands tenderly, right? Let's assume. Then at a certain moment, something happened and they pushed each other, right? And started drifting apart. I love you, I hate you, transition between those two states can be very fast, right? So what else we know? We also know that the travel time of one person to the edge of this ring is given, let's say 20 seconds. So the problem is we need to find the travel time of the second person. Of course, masses are given of these two skaters. So let me start first again with the picture. Then I will write down what is given, and then we will start discussing. So first of all, system is. So our system of two objects, two skaters. So we have two skaters. Okay, so we have a circular ring. Right. So circle. Okay, good enough. Right, so here is the center. Right, and we have two guys, right, on skates, holding hands. Right, and here is the second one. Right. Okay. So next, of course, I need to introduce coordinate system because again, linear momentum is a vector. So coordinate system is crucial. Wait, but not as bad as this. Okay, let me redraw it. Okay, so that my y direction, this is my x direction. So coordinate system. Now, before I start giving any numbers, let's label somehow this person and that person. Since this person is on the right side of the picture, let's call it the rightist. Right? So this will be my rightist. Right? And since this person is on the left side, let me call it leftist. Right? Yes, so maybe that's why they split up. Rightist and leftist, it's not very stable couple, right? It's very unstable. Okay, so let me give you some numbers. So the mass of the rightist person is, I think, 75 kilograms. Mass of the left person, 50 kilograms. Then, of course, their initial velocity is 0, right? No, velocities, let me draw the red in the red because it's important. So V left initial equals to V right initial equals 0. So their initial velocities are 0 because they're standing at the initial moment of time. Now, when they started drifting apart, of course, let's label those velocities. VR final. It's the velocity of the rightist after they split up. And let me label this velocity as VL final. Then, as I said, there is another piece of information that this person, the heaviest, the rightist, it takes 20 seconds for this guy to reach the edge of the ring. And of course, basically it covers radius, this distance. So let me draw this. So this is R, and it's actually given 30 meters. And we know the travel time of the rightist person is 20 seconds. Okay, let me remove this. Okay, 20 seconds. So that's what is given. So now we need to find the travel time of this left person, TL. Right? So that's our unknown. Okay, again, we have one-dimensional motion, two objects. We can apply what we reviewed like at the very beginning. So what we used in this problem, so that the net force, external force, acting on the system in a certain direction, we're going to use, of course, x direction because our motion in the x direction. So net external force acting on the system equals to the rate of change of the total linear momentum in the x direction. So now, we need to understand what will happen with the linear momentum. Is it going to be conserved or not? So we need to analyze all external forces acting on this system. Again, system are these two skaters. Of course, forces in the x direction. So which forces in the x direction can we have? Air resistance, okay, negligibly small. Then friction, we assume that ice is good, skates are good. So no friction, as a result, no external forces acting on the system, and the total linear momentum in the x direction must be constant. Again, internal forces, their forces that they exert on each other, those forces are not capable of changing the total linear momentum. All right. Okay, so now I can write, since again there is no friction, I can write, so the net external force in the x direction equals 0, and then as a result, the total linear momentum in the x direction is constant. So px equals constant. So conservation of linear momentum, conservation of linear momentum. Okay, so now let's apply that conservation of linear momentum. First, I will write P total linear momentum. Let me start with final, right? Final in the x direction must be equal to the total linear momentum initial, of course, in the x direction. So that will be basically our starting point. So now we need to write explicitly. Of course, we need to keep track of the directions, right? This person moves this way, this person moves that way in the negative x direction. So we have to write down properly this total linear momentum. So final, the right person, MR, travels in the positive direction, so the linear momentum is positive. So I can write MR, VR, final. I introduce in the equation with plus, because again, linear momentum of the right person is positive. Then, contribution to the total linear momentum from the leftist, ML times velocity of the leftist final. And this guy travels in the negative x direction. So I have to put minus in front, right? Because velocity is negative and the total, and the linear momentum of the left person is also negative. So I will put minus. Okay, then, initial state. They were standing together at the center of the ring and they did not move, right? So I can write that MR, V, R initial, and of course this is 0. Initial velocity of the right person was 0. In plus left V, L initial, of course this is also 0. So this side is just 0. So it is equal to 0. Now, this left-hand side, let's look. These velocities are not given, right? These velocities are not given. So we need to write them in terms of what we know. And we haven't used this fact so far. We haven't used that the travel time of the right person is 20 seconds. Moreover, we know since there is no forces acting in this direction, this motion is going to be uniform. Uniform translational motion. It means this right person is going to move with a constant velocity. And of course the same we can say about the leftist. Right? So this distance r is covered in this period of time with this velocity. So we can easily write r equals v r final times the travel time of the right person. Of course, we need to get velocity in order to plug in our equation. So let's write Vr final equals r divided by the travel time of the right person. So we can take this and plug it in our equation. Okay. Very similar, we can tell about this person, right? I can also say the motion of the leftist is uniform with this velocity, and we know the distance r. So I can write exactly the same expression. R equals v left final times the travel time of the left person. Of course, the travel time is not given, but that's how we're going to introduce in our equation our unknown, which we need to find finally. So now I can also solve it for VL final. It will be R divided by the travel time of the leftist. And again, I will take this and plug it in our equation. Right. So we're almost done. So let's just rewrite this equation with these contributions and see what we can get. Right. So MR, wait, no, we're going to replace the R. It will be R over travel time of the right person. So it's just this first term, and instead of velocity, I introduce this. Minus mass of the left, and now again, instead of velocity, I will write this ratio R versus the travel time of the left, and it is equal to 0. Radius can be cancelled. And it surprised me because this radius is actually given. Right. But we don't need that radius in order to solve this problem. So finally, let's just move this term to that side. So it will be MR divided by TR equals to M sub L divided by T sub L. Again, so everything is known except for the travel time of the left person. So let's solve it for TL. So TL would be equal MR divided by, no, ML divided by MR. ML divided by MR times the travel time of the right person. So that's the algebraic expression of the final answer. And now if we plug numbers, we're going to find the answer. Okay, let me plug numbers. So it will be TL equals mass left 50 kilograms, the right 75 kilograms, and time, the travel time of the right person, 20 seconds. 20 seconds. Okay, if you calculate, I will look at my notes, it is 13.3 seconds. So that's the final answer. So that's how much time it takes for the leftist to reach the edge of the ring. Right. So that's the problem. Another example, how conservation of linear momentum can be used to analyze situations, to solve problems. Again, so every time, first you need to look at the external forces. If the net external force in a certain direction is 0, it means that linear momentum, total linear momentum in that direction is preserved, is conserved, constant. Right? And then you can apply. Of course, as I said, sometimes linear momentum in a certain direction is constant, but linear momentum is in different direction is not constant. But of course, in this case, conservation of linear momentum in the x direction was enough to solve this problem. Okay, guys. Next problem, 1153. 1153. Now it's about a bullet and a target. Target, it can be, let's say, a massive wooden block. So now let me write, so what is our system? It's a bullet plus a target. Right. So what's the physical situation? So we have a massive wooden block. much heavier than the mass of the bullet, right? Stationary on some frictionless surface, for example, on the surface of ice. So no friction. The surface is very smooth. Then you'll take and fire a bullet into that wooden block. All right, and it happens that the bullet manages to get through the wooden block, right? So making a hole. And we also know that we also know the final velocity of the bullet, right, after the impact. So the question is, what's the final velocity of the target, right? So initially, the target is at rest, bullet is flying. After the impact, after the collision, a bullet is still flying and the target will be sliding. So we need to find the velocity of the target after the impact. Again, it's a one-dimensional problem, right? So I will introduce x-axis along the direction of motion, right? Along the horizontal direction. So let me draw this situation, right? So first we have, right? Okay, it's not horizontal. Let me draw better. Right, so let's see. This is my horizontal surface, x, so which is smooth, right? So no friction. Right. And here's my wooden block, massive wooden block, which is a target, right? So that's my target. And let me label it. Mass is okay, I will write it here. No, you know what? I will right. Mass of the target is 350 kilograms. I just want to write all the numbers again on the picture. Then here comes the bullet, right? So bullet, right? Mass of the bullet is 25 grams, right? And the initial velocity of the bullet is given. So the bullet initial 1200 meters per second. So it's fast. 1200 meters per second. So that is our initial situation. So that's our initial situation. Yeah, and of course, initial velocity of the target, the target initial is 0, right? So the target is at rest. Now the final situation. All right, so again, our smooth surface, x direction. Let's say target moved slightly. All right, so again, it's still the same. Of course, it will lose some mass, the target, right? So let me draw the hole, right? So that is the hole in the target. Of course, there will be some loss in the mass, right? Because the bullet will make some hole, right? But since the mass of this target 350 kilograms and bullet is 25 grams, so that loss in the mass will be very small, right? So we can neglect that. We can neglect it. So and of course the bullet will continue traveling, but now, of course, with the same mass, we assume that bullet did not lose any mass. And the final velocity of the bullet is given. The bullet final equals to 900 meters per second. And what we need to find, the velocity of the target final. Okay, let me circle it. That's what we need to find. Okay? Yeah, and of course, this is our final situation. So that is initial, that is the final situation, right? So everything is on the picture, what is given, right? The physical situation. So now let's start analyzing. Again, we have one-dimensional motion, right, of two particles, and we showed in the review that the net external force in the x direction equals to the rate of change of the total linear momentum, right? Again, I'm trying to justify that the linear momentum will be conserved. So let's look at all external forces acting on the system in the x direction. Bullet. Of course, it has to go through air, right? But we can, with very good approximation, we can neglect the resistance of the air. Right? Then, of course, there will be gravity, but the gravity in the vertical direction, which is not going to affect the motion in the x direction. Right? Then, the target, the wooden block. Friction. Possible, but we assume that the surface is smooth, icy surface, for example, right? So there is no friction force, right? And so there are no any other forces in the horizontal direction, external forces in the horizontal direction. So we can write, since net external force in the x direction equals 0, I will write no friction. No friction. That's the major candidate for to ruin conservation of linear momentum, right? Then, since no friction, so as a result, we can write that the total linear momentum in the x direction is preserved. Conservation of linear momentum, right? So now, as a result, we can write. So total linear momentum of the system initial equals to the total linear momentum final, right? So that is basically initial point. But of course, I want to justify every time why is linear momentum conserved, right? Because the net external force in the x direction is 0. All right, so now let's write explicitly what we have here. Bullet travels in the positive x direction, so velocity is positive, linear momentum positive as well. So it will be m bullet v bullet initial, positive, right? Target, mass of the target, velocity of the target initial, and of course velocity of the target is 0 initial, so we can dump this term, v target initial equals 0. Then, after the impact, after the collision, right, so let me start with the bullet. Bullet still travels in the positive x direction. It is given in the problem, right? So I can write it is equal, so mass of the bullet times velocity of the bullet final, and of course it goes with plus into the equation because it travels in the positive x direction. Target, we don't know, so let's assume it's positive. If it's not positive at the end, we will get negative velocity, right? Mass of the target and velocity of the target final, right? So that is our unknown. So let's see. Mass of the bullet is given, velocity of the bullet initial is given, this also given, this is given, that is given. Okay, one equation, one unknown, it can be easily solved. Right? We can easily solve for the final velocity of the target, right? So let me just solve it for that. Okay, I will take this term, right? Yeah, I will take this term and move it to the left-hand side of the equation, right? So I will end up with mass of the bullet, velocity of the bullet initial, minus mass of the bullet, velocity of the bullet final, equals to mass of the target, velocity of the target final. I'll just move that term to the left-hand side, that's it. Then, of course, I can factor out mass of the bullet because it's exactly the same, right? And I will take these factor mass of the target and bring it to the other side. So it will be V target final equals mass of the bullet divided by mass of the target, velocity of the bullet initial minus velocity of the bullet final. Okay, so that is the answer, algebraic form of the answer. You can frame it. Right. And now let's plug numbers. Right. So V target final equals mass of the bullet 25 grams, but of course we have to convert it into kilograms. So it will be 25 times 10 to the power of minus 3 kilograms divided. Mass of the target, 350. 350 kilograms. And the difference between the velocities of the bullet, initial and final. Initial is 1200, final is 900. Right, so let's write it down. So 1200 meters per second minus 900 meters per second. Right, it will be. So you can calculate. I will use my notes. 0.021 meters per second. 0.021 meters per second. So, first of all, of course it's small, because this target is very heavy, right? Of course. And this velocity is positive. Positive velocity, it means that our target is sliding in the positive x direction, right? So positive, maybe I will write it. So it's slides in plus x direction, right? Positive. Okay, again, every time, all these three problems, the structure of the solution is exactly the same. So first I identify the system every time we have two objects. Then I'll draw the pictures. Then this equation, and every time I would analyze external forces acting on the system, right? And every time it was external forces in the x direction. If net external force in the x direction is 0, then total linear momentum in the x direction is preserved. And then I will write this every time, then write down explicitly mv, 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 but of course with the proper signs. We just need to look carefully for the directions. If object moves in a positive x direction, contribution to this equation is positive. If object moves in the negative x direction, of course, contribution must be negative, right? And then start analyzing, right, and solve, if it's possible, for whatever it needs to be found. Okay, so that's it. Thank you. All right. I think that's all I was planning to tell you.